Welcome back. This is at THS Mr. Jones, and we're going to talk about chapter 5.2. 5.2 deals with logarithmic functions and their graphs. Okay, and let's talk about what is a logarithm. So a logarithm is y equals log of a base b of x. Now, we also at this time want to talk about why we have logarithms. Okay, now log and logarithms are the exact same thing. The reason we have logarithms is because if I have some equation like this, let's say b y to x, okay, so this is some sort of exponential here, okay, because in this case, this is my variable. But in order to undo this exponential, I have to have a logarithm. Okay, so in fact, this is the exact same thing as this. Okay, we'll get in later to solving exponentials. Okay, but in order to solve exponentials, we have to have logarithms that undo it. Okay, just like here, we have the plus and the minus are inverses of each other. And over here we have the square root and the square are inverses of each other. Likewise on the calculator, we have ln undoes 10 to the x, which is exponential, or log undoes 10 to the x, and ln undoes e to the x as exponential. Okay, so the reason we have these logarithms are so that we can undo exponentials. And in order to go between logarithms and exponentials, we use this right here. So just for a quick example here, if I give you something like log base 2 of 8 equals 3. Now this is a solved equation here. This is our base, okay, and this sometimes could be in parentheses or not. We take our base, okay, this base goes here. Okay, so we've got 2 to the exponent. The answer is my exponent here. So I've got 2 to the third equals 8. Okay, and in fact, 2 to the third equals 8. Well, also, the log of base 2 of 8 equals 3. So exponents and logarithms are very similar. They are inverses of each other. Now, there's a couple special things we need to know about logarithms. So let's go back to f of x equals log b of x. So x in here, x has to be bigger than 0. Okay. B will also be bigger than 0, and it will not be 1. Okay, that's what we talked about logs with this. With exponentials, this b has to be bigger than 0, but not 1. Remember, it can be a fraction or a whole number from decay, growth and decay. Now, sometimes these transitions here can get a little bit more tricky. For example, let's say I had something like this. The square root of 81 equals 9. So now I can give you the exponential here, and we can move it back to logarithm. Now we know this is true, right? But what is this power here? Well, this is 81 to the half power equals 9. Okay, so we're going backwards. So my base becomes the base of the log, so log of 81. Okay, my answer now became inside the parentheses of 9 equals a half. Okay. And we're done with that. So we need to be able to switch between logarithm and exponential very easily, and that's why we do that. Now, we talked about that logs are inverses of each other. So what does that really mean to be an inverse of each other? Okay, so let's say I've got this graph here. And we talked before about the square and the square root being inverses of each other. And hopefully you remember that if two things are inverses of each other, that they are a reflection across the line y equals x. So let's do another one over here because we have both growth and decay. Okay, so let's draw out our exponential curve here. So I have exponential growth. Let's say something like, I got some exponential growth like that. And then over here, we got some exponential decay like that. Some parent function there. So the inverse of exponential is logarithm. So these logarithmic graphs are just going to be a reflection over that line. So in this case, they'll look something like this. Okay, this could be, I don't know, this could be, let's say, f of x equals 2 to the x. Okay, and this might be f of x, if it's the inverse of that, would be log base 2 of x. Notice the bases match. So then this one could be f of x equals 1/2 to the x, since it's decay. Then if I reflect it across, it's going to look something similar to this. And this could be log base 1/2 of x. Okay, so we're flipping it over that x-axis. We also talked about how domain and range are related. So let's add in our domain and range here for these. So the domain of this one would be, so domain, now let's just do it in marker here. So the domain is -infinity to infinity, but the range here is 0 to infinity. Okay, same thing for this one, -infinity to infinity, 0 to infinity. Now when we talk about inverse and how the domain and range relate, well, this domain of these logarithms will be 0 to infinity. And the range now is -infinity to infinity. Notice that the ranges just flip-flopped. Okay, that's what happens, okay, with inverses. X and Y switch on everything. Okay, notice instead of having a horizontal asymptote, now I have a vertical asymptote. Same thing over here. We can still move these down, you know, move them up, right, left, down. So let's say f of x equals a log base b bx minus h plus k. So there's our parent function, and the order is h b a k. Holler back. Okay, holler back. That's how we'll remember that. Okay, so that's the order we go in. Again, this b is just your rate. Okay, so again, this moves it left and right. This is a horizontal stretch or shrink. This is a vertical stretch or shrink, or over x. This one's over y, and this is moving it up, down. We can still do the same thing. Now, back with domain, since my domain of logarithms is restricted here, this value becomes very important. Okay, notice here, right here, I said that value has to be bigger than 0. So this value has to be, so bx minus h has to be bigger than or equal to 0. For example, if I want to find the domain of this, let's say I've got log 3 2x minus 5. That's my function. Okay, it's a base 3. It moved right 5 and got a horizontal stretch of 2. Okay, but I want to find the domain. I know the range is negative infinity to infinity, but I want to know the domain. Well, we're going to take this here in parentheses. 2x minus 5 has to be bigger than 0 by definition. Okay, so then we'll add 5 and divide by 2. So x is greater than 5 over 2. So then we have 5 over 2 comma infinity is my domain. And that's how we get it. A little bit easier than the exponential. Okay, so again, practice on, knowing this up, down, left, right, stretch, shrink. That basically sums it up. Okay, we'll have some application problems we'll discuss in class. So here are your 4 questions here. So how do you go from logarithmic to exponential form? Why do we need logs? Graphically and algebraically, how are logs and exponents related? And what happens in this logarithmic function? Okay, that's like, what's the parent function? How does it get shifted? Okay, quite a few suggested problems here. Because this is somewhat of a newer / difficult topic, I want to make sure you get enough practice. So again, this is the stopping point for class. Make sure you get your questions finished, and I will continue on this video for the entire lesson. Okay, so let's back up just a little bit, and let's do a few more examples of logarithms. Okay, so again, let's say we have log 9 of 3, log base 9 of 3 equals 1/2. And I want to change that into the other form. Okay, since it's in log, we're going to go to exponential. In order to do that, we're going to take our base is the same, and we're going to take it to this power, and it will equal that number. So in this case, we have 9 to the half power equals 3, which is also saying the square root of 9 is 3, which we agree with, should agree with. Okay, let's try the other way around. Let's say we have 16 equals 2 to the 4th power. So now when I go this direction, okay, we have log. Again, the bases are the same. Base 2 of 16 equals 4. And we can kind of check this. 2 to the 4th equals 16. 2 to the 4th equals 16. Okay, so have to be able to go from logarithm to exponential and exponential to logarithmic. Okay, we can also solve logarithms doing this. Okay, so let's say we have log 3 of 81. And what does that equal? I want to know, what does that equal? So we'll change it to exponential. We'll say 3 to the x. So 3 to the x equals 81, equals that number. So 3 to what power will give you 81? Well, 3 times 3 is 9, times 3 is 27, times 3 would be 81. So I had 1, 2, 3, 4. So in this case, x equals 4. So log base 3 of 81 equals 4. Okay. These are a little bit tricky. Let's try another one. Let's say log base 5 of 1/5. Now I want to know, what does that equal? So we'll say equals x. So we'll change it. 5 to the x equals, so 5 to the x equals 1/5. Ooh, a little bit tricky. you have to understand what kind of exponent makes it into a fraction. Okay, that would be a negative. Well, since the 5 didn't change, we know that that would be a power of 1. So in this case, x is minus 1, because 5 to the minus 1 is 1/5. Okay. Now, we can do some of these on the calculator. If you notice here, we have an ln button and a log button. Okay. If it does not have a base, let's say we just put log of 100. Since it doesn't have a number there, it's an automatic 10. Okay. ln is the same as log with base e. Okay. And those two are very commonly used. That's why you see it here on the calculator. Okay. But if I have something other than 10 or e, I can't put it into the calculator yet. We'll talk about it later on. Okay. So let's look at something like this. Let's say ln of minus 2. Okay. Well, if I go to put that into the calculator here, so ln of minus 2 equals non-real answer. Well, if you remember me saying a little bit ago, this in here has to be bigger than 0, which in this case it is not. Hence why we cannot evaluate that number. Okay, so that has a non-real solution. Okay, we talked a little bit about finding domain. So let's say find domain for f of x equals, let's try something a little bit harder. Log x squared minus 9. Okay, so this value right here, x squared minus 9, has to be bigger than equal to, or bigger than 0. Okay, so if I solve that, we'll add 9. So x squared is greater than 9. Square root. You have x is bigger than plus minus 3. Okay. So if it's bigger than, so we'll say we actually have a union here. So it's bigger than 3. Okay. And this is kind of hard to read, but since it's bigger than negative 3, it actually means less than negative 3. Okay. Again, this would be 3 would be our negative 3 and 3. That would be our changing point. So then we'd have to pick 3 numbers in here. So I might pick minus 10, 0, and 10, and pick and see which one's true. That'd be false. That would be true, to figure out which ones work. Okay, so don't forget how to solve quadratic inequalities. So here is our domain for that situation. Now, if we move on to some of the more graphing, so graph f of x equals minus log base 2 x minus 3. Okay, so we'll start with parent function. That would be log base 2 of x. Okay, and then we still do B-A-K. So h would be right here. There's no h. Sorry, h is right here, which would be right 3. There's no b. Then we go to a, which is over x, since that's negative. And there's no k out here. Okay, so it's log base 2 of x. We go right 3 and over x. So if we have our graph here, Now, some of these parent functions are in your book, okay? So you'll need to know those for a little bit. So this right here is our parent function. This is log base 2 of x, parent function. So we're going to move it right 3. So 1, 2, 3. So it'd be something like that. And then we flip it over the x. So it kind of flips upside down here. Okay, so this will still be it's a little wrong. This right here will still be my vertical asymptote. Since I moved it over 3, that vertical asymptote shifted over 1, 2, 3. Sorry, that should be right here. Shifted over 3 spots. So then we're going to flip it over. Let me just redo it. So it was here. It crossed at 1. Okay, so this vertical asymptote, when I move it right 3, goes 1, 2, 3. So here's my vertical asymptote, and my graph's now here. Okay, so then we're going to flip it upside down or flip it over the x. Now we're looking at this graph. Okay, and we still want to be able to say domain and range. Okay, again, for logarithms, the range is minus infinity to infinity, which is a domain of exponentials. In this case, the domain starts at 3 and goes to infinity, which is solving this. X minus 3 is bigger than 0. Add 3, you get x greater than 3. Those two are the same. Okay. Now, there's some formulas we can use logarithms in. And some frequency and some application problems, decibels. So let's look at something like that real quick. We'll just do one example because there's a wide range of problems. So let's look at decibel, sound. So we'll look at sound here. So decibel equals 10 log I over IT. So D is a decibel level. Okay, so you got your log. I is the intensity. And this I is the intensity threshold. Okay, of a human. This is depending on what you're comparing it to. So we're going to compare it to a human, and we're actually going to use 1 times 10 to the negative 12 watts per meter squared. Okay. So just a quick example. So suppose you have seats to a concert given by your favorite music artist. Calculate the approximate decimal level associated with the typical sound intensity given I equals 1 times 10 to the negative 7 watts per meter squared. Okay, so all we're doing is just taking this number and plugging it in. These get super easy. So density is 10 log. So they gave me I, 1 times 10 to the minus 2, over, I'm already given that, times 10 to the minus 12. So we can just really just kind of work that out. So we'll say 10 log. Okay, so these are the same. So if I were to move this up, that would be a plus 12. Okay, so I've got negative 2 plus 12. That would be 10 to the 10th. Okay, now since this does not have a base, it is to the 10. We could also just put this into the calculator. Okay, let's just stop and put this part into the calculator. So I have 10 log, and it's already a base 10, 10 to the 10th. Oop. 100. So your decibel level, and we'll get into more of how we should be reducing these later on. So your decibel level is 100 decibels. The other application for this problem is Richter scale. We can do some frequency stuff too, but let's focus here on the Richter scale for just a second. So Richter scale. So we have M equals 2/3 log E over E naught. Okay, so M is magnitude. E is the seismic energy released. And E naught is your reference earthquake. Okay, so this again is a constant like it was earlier. So this is 10 to the 4.4 joules. So a problem you might see like this would be you had an earthquake that released approximately 1.12 times 10 to the 15th joules of energy. Where does it rank on the Richter scale? This was actually an earthquake in 1989 at the World Series, or during the World Series. So all I got to do is put that up here. So I have magnitude, or your number on the Richter scale, 2/3 log. This is the one that they're giving me in the problem. And this is my constant, so 10 to the 4.4. So I can just plug that in here. So we'll say 2/3 log. And then, so we're going to put this in parentheses. So 1.12 times 10 to the 15th divided by 10 to the 4.4. Enter. So then I get 7.1. So that's what it's going to be on the actual Richter scale. Okay, so that concludes 5.2. Again, here are your suggested problems. Okay, take a look at them. Let me know if you got questions. Be ready for your quiz. As always, this is at THS Mr. Jones signing off. Thanks for watching. Make sure you subscribe and like.